All right, let's talk about a classic coding problem. It's one of those that seems pretty simple on the surface, but it actually hides a really elegant and super efficient solution. We're going to be counting bits, so let's just dive right in. So picture this, you're in a coding interview, or maybe you're trying to optimize a piece of software where every millisecond counts. Your task? Count the number of ones in the binary version of every single number all the way up to 100,000. And here's the kicker, it has to be fast. So where do you even begin?
Okay, so let's get specific about what we're trying to do. We're given a number, let's call it n. The goal is to build an array, we'll call it ands, and for every position in that array, say ands I, it needs to hold the count of ones for the number I. And we do this for every number from 0 all the way to n.
This table makes it super clear. So if n is 5, we just go number by number. Take 3, for instance. In binary, that's 1, 1, so it's got 2 ones. Then you look at 5. In binary, that's 1, 0, 1, so it also has 2 ones. In the end, what we're trying to build is that array of counts at the bottom. 0, 1, 1, 2, 1, 2. Seems simple enough, right?
So what's the first thing that probably pops into your head? Well, for most of us, it's about finding the path of least resistance. And in programming, that usually means letting the language's built-in tools do all the heavy lifting for us.
The logic here is about as straightforward as it gets. You just set up a simple loop that runs from 0 all the way to n, and for each number in that loop, you just call a handy function that's already built to do exactly what we need, count the bits.
And you can see just how easy this is. Pretty much any modern language you're using has one of these ready to go. C++ has its __ built-in pop count, Java has integer.bit count, and so on. You literally just plug it in, and it works. But is it actually fast enough for our challenge?
And right there, that's the catch. This is the kind of follow-up question that really separates a decent solution from a great one. See, that simple approach runs in what we call O(n) log n time. That's because for each of the n numbers, counting the bits takes a little bit of work. The real challenge is, can you do it in O(n), or linear time? Basically, in a single pass, no messing around.
This is where it gets really fun. We've got to think beyond just brute forcing it. We have to be smarter. How can we avoid recalculating everything from scratch for every single number? Well, the secret is all about finding a hidden pattern.
And this is it. This one line of code is the entire key to the super fast solution. I know, it looks like magic, right? It's basically saying that the answer for the number we're on, I, is directly related to the answer for some other number we've already solved. But what is that other number? Okay, let's just pause on the most important question here. What on earth is this I and I-1 expression actually doing? That little ampersand is a bitwise AND operator, and this specific pattern is a pretty famous trick in the world of bit manipulation. Understanding this one little piece unlocks the whole puzzle.
So it's time to pull back the curtain and see what's really going on here. This is the part where everything is about to click into place. Get ready for that aha moment.
Let's just trace this with a real example. Let's take the number 6, which is 110 in binary. Now the number right before it, 5, is 101. When you do a bitwise AND, you compare them bit by bit. A 1 only survives if it's a 1 in both numbers. So 110 and 101 gives us 100, which is the number 4. Now pay close attention to what just happened. 110 turned into 100.
So here it is, the big secret. That expression, I and I-1, will always take a number and just turn its rightmost 1 bit into a 0, every single time. In our example, the rightmost 1 in 110 got flipped off, turning it into 100. This is the golden nugget of information we've been looking for.
Okay, so now we know the trick. The next step is to actually put it to work. Let's see how this one clever insight becomes the engine for our incredibly efficient solution. The logic here is just beautiful. First, we now know that I and I-1 is just our current number, but with one less 1 bit. Second, because this new number is smaller than I, we must have already calculated its bit count and stored it in our results array. And third, that means the bit count for our current number I is simply the answer we already found, plus 1 to account for that bit we just turned off. And this table shows it all in action. To get the answer for 3, we look at 3 and 2, which gives us 2. We've already calculated the answer for 2, it's 1. So the answer for 3 is just 1 plus 1, which is 2. Let's do 5. We look at 5 and 4, which gives us 4. We already know the answer for 4 is 1. So the answer for 5 must be 1 plus 1, which is 2. We're literally building on the answers we've already found. It's the whole idea behind dynamic programming.
So we've seen the how, but it's just as important to understand the why. Why does going through all this trouble for one little bitwise trick actually matter in the real world?
I mean, just look at the difference. We went from a simple brute force loop to this elegant and way faster dynamic programming approach. The complexity drops from O of n log n to a clean O of n. Now, this isn't just for fun. When n is a huge number like 100,000, this is the difference between code that's just okay and code that's truly exceptional.
And that really leaves us with a final thought, doesn't it? This whole problem shows that sometimes the most complicated-looking challenges are actually hiding a simple, elegant answer. It all just comes down to finding that one clever insight, that one little trick that changes how you see everything. So, what problems are you working on that might be waiting for their own aha moment?